Welcome back to TalkTensors, the show where we try to, break down all this new machine learning research. We've got a really interesting paper today exploring FMCW radars and feature maps for activity recognition. It's a benchmark study, and we thought this would be a really good one to kind of dive into.
Yeah, definitely. I mean, it's a really interesting take on the whole human activity recognition problem.
Right. HAR.
Yeah, exactly. HAR, as it's known.
And, this one kind of moves away from, I guess, the usual suspects like wearables or cameras and explores using radar.
Yeah, and specifically, they're using frequency modulated continuous wave radar. So FMCW.
FMCW. Okay, so like a lot of people might be thinking, okay, radar, we use that like for tracking airplanes and speeding cars and stuff.
Right.
But it turns out that this technology, it's actually commonly found in a lot of cars now for adaptive cruise control.
Yeah.
It can be repurposed to kind of understand human actions.
Yeah, exactly.
So, I mean, think about it. Wearables can be super uncomfortable.
Yeah, they can be a pain.
You have to charge them all the time.
Right.
Cameras obviously have all sorts of privacy concerns.
Then why is it privacy concerns? Yeah.
And other sensors just have their limitations, right?
Exactly. Yeah.
But radar, I mean, it can work in the dark, it can work through walls and from a distance. So that makes it pretty compelling.
It does. Yeah, absolutely.
So these researchers, they actually built a system using one of these radars.
Mm-hmm.
It was an Infineon BGT60R30C FMCW radar.
Mm-hmm.
And they pointed it at people in a bedroom setting.
Okay, interesting. A bedroom setting, so like a home environment.
Yeah, and they collected data on 7 different activities like walking, sitting, lying down.
Okay.
And even those tricky transitions between actions.
Ah, yeah. Those are always the hardest ones to get, right?
But here's where things get really interesting.
Uh-huh.
They didn't just look at the raw radar output like an image, which is how a lot of people do it.
Right.
Instead, they extracted these things called feature maps.
Okay, so what are these feature maps exactly?
Well, think of them like
blueprints.
Yeah, or like a 3D snapshot of how the radar signal is changing over time and space.
So it's not just where someone is, but how they're moving.
Yeah, exactly. And they have 3 different ones: range Doppler, range Azimuth, and range elevation.
So each one captures a different aspect of the movement.
Mm-hmm. They provide a much richer understanding of what's actually happening.
That makes sense.
And then they took these feature maps and they fed them into a bunch of different machine learning models.
Okay, so like the classic models like SVM and MLP.
Yep. And also the big deep learning models.
Ah, okay, so like CNN, LSTM, Conveilistium.
Yeah, all the heavy hitters.
Yeah.
And they wanted to see which model could best decode the activities.
Interesting. So it's like an algorithmic showdown?
Yeah, totally. Like who's going to be the best activity recognizer?
I like it. And who won?
Well, it was actually Conveilistium.
Yeah.
It just consistently outperformed the others.
Especially when using all 3 of those feature maps, right?
Yeah, exactly. And that's not a coincidence. I mean, Conveilistium is really good for this kind of data because it can understand both the spatial and temporal aspects of movement.
Right. It sees not only where things are happening, but how they're changing over time. So it's like it has a sense of the flow of the movement.
Yeah, it's pretty cool. And the results were really impressive. I mean, the system got over 90% accuracy for recognizing 7 activities.
Wow, that's pretty high.
Yeah, and when they narrowed it down to just 4 activities, the accuracy jumped to almost 98%.
Okay, so that suggests it's really good at distinguishing between very specific movements.
Yeah, but they didn't just stop there. I mean, to make sure these results weren't just a fluke, they used 2 different validation techniques.
Okay, what kind of techniques?
So first, they trained the model on data from some rooms and tested it on others.
Right, so cross-scene validation.
Exactly. Then they did something even cooler called leave one person out cross-validation.
Ah, so they trained on data from 2 people and tested it on a 3rd person.
Right, and guess what? Conveilistium aced both tests.
Wow, so that means it's not just memorizing specific movements or environments, it's learning something more fundamental about how people move.
Exactly. It can generalize across different people and settings. So to really understand the impact of this research, I think we need to kind of step back and look at the history of activity recognition.
Yeah, that's a good point. It's helpful to see how we got here.
So, activity recognition has been a hot topic for a long time. I mean, researchers have been trying to understand human actions for decades.
Yeah, that's true.
And those early attempts often relied on wearable sensors, like you'd find in a fitness tracker or a smartwatch.
Right. But those have their limitations.
Yeah, I mean, who wants to wear sensors all the time?
Yeah. Plus, they need to be charged, and they're not always suitable for every situation.
Exactly. Then came the video-based systems, which could capture a much wider range of activity.
But then you run into privacy issues.
Big time.
I mean, imagine cameras watching your every move in your own home.
Yeah, not ideal.
Not at all. Plus, video requires a lot of processing power, and it doesn't work well in the dark.
Right. So that's when researchers started looking at other types of sensors. And that's where radar started to emerge as a promising alternative.
Yeah, radar seems like a good middle ground. It's less intrusive than cameras and more versatile than wearables.
Exactly. And, early radar systems were really bulky and expensive.
I mean, they were mainly used for things like air traffic control or weather forecasting.
Right. But thanks to all the advances in microelectronics and signal processing, we now have these compact, affordable radar sensors that can pick up even the tiniest movements.
So it's kind of like the evolution of computers, right?
Yeah, totally.
We went from these massive room-sized machines to powerful devices that fit in our pockets.
Right.
And now we're seeing that same kind of miniaturization happening with radar technology.
Exactly. And that's why this paper is so exciting. It shows that we can use these readily available radar sensors to achieve really impressive results in activity recognition.
And it opens up a whole new world of possibilities for how we can use this technology.
Absolutely.
I'm really curious to see where this research leads.
Yeah, me too. It's
Yeah.
definitely a field to watch.
For sure. Yeah, so one of the big challenges with radar, for activity recognition, it's all the noise.
Noise, like what kind of noise?
Well, all the random reflections bouncing around the room, like furniture walls, even pets wandering through.
So it's like trying to hear a whisper in a crowded room.
That's a great analogy, yeah. Like, how do you filter out all that clutter and just focus on the human movements?
Did they use some kind of noise-canceling headphones for the radar or something?
Well, not exactly headphones, but they did have to use some pretty clever signal processing techniques to isolate the signals that were coming from the person. One of the techniques is called the moving target indicator, or MTI.
MTI. Okay, and what does that do?
It's like a filter that specifically targets moving objects and ignores stationary ones.
So it's kind of like a spotlight that's only shining on the things in motion.
Exactly. It helps to isolate the signals that are coming from the person who's doing the activity.
That makes sense.
They also use something called a Blackman-Harris window function, which is a way to kind of smooth out the data and reduce noise even further.
Okay. That sounds pretty technical.
It is a bit technical, but the main takeaway is that they use a combination of signal processing to clean up the data before they fed it into the machine learning models.
So like a lot of behind-the-scenes work to make sure the data was good.
Yeah, exactly.
Now, they only use data from 3 participants in this study.
Right.
Is that really enough to train a model that can recognize activities for like a wider population?
That's a good question, and it's something they actually addressed in the paper. 3 participants is not a huge sample size.
Right.
But they were very careful in how they collected the data. Remember those 16 trials and 7 different activities?
Yeah.
They made sure to include both, common things like walking and sitting, and also more subtle things like lying on a bed versus lying on the floor.
Oh, wow. Okay.
And they also captured those transitions between activities.
Yeah, those subtle movements we make as we're like shifting from one action to another.
Exactly.
Yep.
Because we don't just go from standing still to walking instantly.
Right.
Right? There's a whole sequence of micro movements involved.
Right.
And capturing those transitions is really important for building a system that can accurately recognize activities in the real world.
So even with just 3 people, they managed to get a pretty diverse data set.
Yeah, they did. And then to make sure the model could generalize to more people, they used those validation techniques we talked about earlier.
So cross-scene validation
Right.
and the leave one person out cross-validation.
Right, exactly. So they trained and tested their models on different combinations of rooms and participants.
To see how well it could handle variations in environment and like individual movement patterns.
Yeah, exactly. It's like they were putting the model through boot camp.
I like that analogy.
Throwing all sorts of different scenarios at it.
To make sure it could handle anything.
Exactly. And the fact that Conveilistium model did so well under those tests suggests that this approach has real potential.
Yeah, that's really promising. Okay, so let's go back to those feature maps for a second.
Okay.
Why are they so important?
Okay, so imagine you're trying to find something specific in a really cluttered photograph.
Okay.
It can be hard because there's so much visual information competing for your attention.
Right.
But imagine you had a set of filters that only highlighted the features you were interested in, like the shape or the color or the texture of the object you were looking for.
Okay.
That's basically what these feature maps do for the radar data. They simplify the information and make it easier for the machine learning models to identify the patterns that are relevant.
So it's like those Instagram filters that can make a photo more vibrant or highlight certain features.
Yeah, that's a good way to think about it.
Instead of looking at the whole messy picture, they let the algorithms focus on the parts of the signal that are important for activity recognition.
Right. So, for example, the range Doppler map focuses on how the distance and speed of the target are changing over time.
So it's creating a dynamic representation of the motion. Okay, I'm starting to see why these feature maps are so crucial. They give a much more focused view of the data so the algorithms can do their job better.
Right. And then you've got the range azimuth and range elevation maps, which give you spatial information about where the target is in relation to the radar sensor.
So by combining all three of those maps, you get a really comprehensive view of the activity.
Yeah, it's like having multiple witnesses to a crime, each giving you a different perspective on what happened.
Interesting analogy. Okay, so all this processing radar data and running these complex models, it sounds pretty computationally expensive.
It is.
Could the system actually work in real time, or would there be like a noticeable lag?
That's a good question. And to be honest, the researchers didn't really delve into optimizing for real-time performance in this paper.
So it's like they built a powerful engine, but they haven't quite figured out the fuel efficiency yet.
Exactly. And that's something that future research will need to address, especially if we want to use this technology in applications where speed is critical.
Right, like fall detection or home automation.
Yeah, you need the system to react instantly, not minutes later when it's too late.
Exactly. Okay, well, speaking of real-world applications, let's move on to our novel notions segment.
Always a fun one.
As always, a quick disclaimer. This is just for brainstorming and entertainment purposes only. We're not giving financial advice or predicting the future of science here.
We just like to explore the possibilities.
So this research got me thinking, what if we combine this radar-based activity recognition with another up-and-coming technology, brain-computer interfaces, or BCIs?
Oh, wow. That's an interesting thought. So you're talking about a system that could not only recognize your movements, but also understand your intentions.
Exactly. BCIs are already being used to help people with paralysis, control prosthetic limbs, and even communicate.
Right.
But what if we could use them to create a totally seamless and intuitive way to interact with our environment?
So instead of fumbling with switches or giving voice commands, you could control your smart home just by thinking.
Yeah, exactly.
Yeah.
Like imagine you think about getting a snack and the lights in the kitchen turn on.
Or you think about adjusting the thermostat and the temperature changes.
That would be amazing.
Yeah.
But how do we deal with accidental activations? You know, like what if you just think about getting a snack and suddenly your robot vacuum cleaner starts going crazy?
That's a good point. We'd need some really good filtering to separate intentional commands from random thoughts.
Right, like maybe some kind of mental double click to confirm.
And then there are the ethical considerations too. I mean, a system that can read your mind raises all sorts of questions about privacy and control.
Yeah, definitely. What if your thoughts are misinterpreted or used against you? That's a whole other can of worms.
For sure. But despite all the challenges, the potential benefits are huge.
Absolutely. Imagine people with disabilities being able to control their surroundings and communicate just by thinking.
That would be life-changing.
It would. And it might not be that far off. Research in both activity recognition and BCIs is moving so fast.
Yeah, it's not hard to imagine those two fields merging in the near future.
Okay, so maybe that's a bit far out.
Oh.
But what about some more immediate applications? Like this technology seems like it could be a game changer for elder care.
Oh, absolutely. Imagine a system that could, discreetly monitor an elderly person's movements in their home.
So if there's a fall or like a sudden change in their activity.
Exactly. It could alert caregivers right away.
Yeah, that would give so much peace of mind to both the seniors and their families.
Definitely. Knowing that help is available if they need it.
It could really help people age in place safely and, maintain their independence.
Yeah. Instead of needing 24/7 care, they could stay in their own homes.
And still have that safety net.
Right. And it's not just about emergencies. I mean, this system could also track subtle changes in movement over time.
Oh, so it could be like an early warning system for potential health problems.
Exactly. Like imagine if it could detect a slight change in gait that could indicate the early stages of Parkinson's.
Or maybe a decline in cognitive function.
Right. Early intervention is so important for those kinds of conditions.
It's like having a guardian angel watching over you.
But instead of wings and a halo, it's got radar waves and machine learning algorithms.
I like that. And this technology isn't just limited to healthcare. We were talking about smart homes earlier.
Oh yeah, the possibilities there are endless.
Imagine a home that adjusts the lighting and temperature based on what you're doing.
So if you're reading a book on the couch, the lights dim and it gets all cozy.
But then if you get up and start moving around, the lights brighten up and the temperature adjusts.
It's all about creating a personalized and responsive living environment.
It would be like having a home that anticipates your needs and always creates the perfect atmosphere.
Yeah, and it could even help save energy.
How so?
Well, if the system knows you're not in a room, it can automatically turn off the lights and adjust the thermostat.
Ah, that makes sense. So you're saving money and helping the environment.
Exactly, a win-win.
Okay, so we've covered a lot of ground today, from the nitty-gritty details of this research to all these amazing potential applications.
Yeah, it's been a really interesting discussion.
But before we wrap up, I want to circle back to the core message of this paper. What's the one big takeaway you want our listeners to remember?
I think the biggest takeaway is that this research really highlights the potential of FMCW radar for activity recognition.
Because it's a technology that's been kind of overlooked in this field.
Right. But it has so many advantages over the other approaches.
It's discreet, it works in any lighting, and people don't have to wear sensors or be on camera.
Exactly. And as the technology keeps getting better and more affordable,
we're probably going to see a lot more innovative uses for it.
Definitely. It's an area to watch, for sure.
Well, that's about all the time we have for today. A huge thank you to our expert for breaking down this research and taking us on this journey into the world of activity recognition.
It's been my pleasure.
And to our listeners, be sure to check out the full paper. We'll have a link in the show notes. And we'd love to hear your thoughts on this research and all the possibilities it opens up.
Feel free to reach out to us on social media or leave a comment on our website.
Until next time, keep exploring the fascinating world of machine learning.
And don't forget to keep those tensors talking.
We'll see you next time.